So,
So, welcome back, all of you, to the chapter Hydrocarbons, Organic Chemistry, chapter 13. Okay, so in the morning class, I was talking about this preparation of alkanes. Till there, I had completed, along with the physical properties also. Now, in this class, today's afternoon class, I would like to complete the chemical properties and the reactions of alkanes, the general reactions of alkanes. Now, please remember that alkanes are very, very simple saturated compounds of carbon and hydrogen, and they have they have only either carbon carbon single bonds or carbon hydrogen single bonds throughout, and there is no multiple bond or there is no functional group present in alkane. Therefore, they do not possess much reactivity. They do not possess much reactivity, and because of this, if you want to react the alkanes with other elements or compounds or molecules like oxygen, halogens, then we need higher temperatures. Then only the what you call reactivity of alkanes is possible. Okay, now we know these alkanes, they undergo important reactions, like they undergo halogenation, they undergo halogenation reaction, they undergo reaction with oxygen also. Okay, and these are important for you all. Okay, now looking at the first one, combustion. Look at the first one, it is called combustion. Now a combustion reaction is a chemical reaction. It is a chemical reaction between a substance and oxygen that proceeds with the evolution of heat and light. Now alkanes readily undergo combustion reactions when ignited. When sufficient oxygen is present to support total combustion, then carbon dioxide and water are the products. So here you can see combustion of alkane, methane, C6H14, that is hexane. Okay, it is producing carbon dioxide and water. Now the reactions are exothermic. The reactions are what? They are exothermic in nature. Please keep that in mind. Okay, now after that, the exothermic nature of alkanes combustion reactions explains the extensive use of alkanes as fuels. Natural gas which is used in home heating is predominantly methane normally. Okay, now moving further to the next one, that is halogenation reaction by using a halogen, chlorine, chlorine, bromine or iodine. Now halogenation of an alkane produces a hydrocarbon derivative, haloalkane, in which one or more halogen atoms have been substituted for hydrogen atoms. An example of an alkane halogenation is given over here. So ethane plus bromine, it is forming bromoethane plus HBr. Okay. Alkane halogenation is an example of a substitution reaction. Now you have to keep this in mind. What is a substitution reaction? Yes. Can anybody tell me what is a substitution reaction? What is a substitution reaction? You have heard of substitution reaction in the past. You have heard about substitution reaction in class 8 also, I think. What is a,
replacing one with another.
yeah, replacing an atom already present in a compound with another atom which is more reactive. So to define it correctly, the reactions in which an atom, or you say a group of atoms present already in a compound, they are replaced by some other atom or some other group without bringing any major change in the structure of the compound. It is called substitution reaction. So alkenes generally undergo this type of reaction, which is called substitution reaction in organic chemistry. Okay, now so at the bottom you can see there is a general equation for the substitution of a single halogen atom for each of the hydrogen atom of an alkene. It is given below. So alkane, if I take alkane, like say if I take CH4 and I use a halogen like Br2, okay, like this. So one hydrogen is replaced by one bromine, so it becomes CH3Br plus the hydrogen which is coming out combines with the bromine atom to form HBr. So that is substitution reaction in organic chemistry. Okay, so we will be learning about the what you call mechanism also slowly and steadily in this chapter. Now, moving to the next slide. Moving to the next slide. These reactions are important. Reaction of alkane with chlorine. And now reaction of alkane with chlorine, it happens by a mechanism which is called free radical mechanism. And the free radical mechanism involves the following steps. That is, the first step is initiation, then we have propagation, then we have termination. Let us look at this in detail. Let us look at this in detail. Okay. Now, in the initiation step, a chlorine molecule in the presence of light, ultraviolet light, it undergoes homolytic fission to produce two chlorine free radicals. To produce two chlorine free radicals in the initiation step. After that, propagation, the chlorine free radical, one of the chlorine free radicals now interacts with an alkane, methane, in the presence of UV light, H nu, to form a methyl free radical and hydrogen chloride. Now the methyl free radical again interacts with another chlorine molecule in the presence of UV light to form methyl chloride and another free radical of chlorine. So this goes on. So methyl chloride with another free radical, so it becomes CH2Cl2. It goes on CH2Cl2 over here plus HCl. Again this CH2Cl2 with Cl will form CH2Cl3 and so on. Okay, so this is propagation. It goes on and on. Now for the termination step, if you see the two chlorine radicals which are produced, they recombine with each other to form chlorine molecule. The the methyl free radicals which are produced, two of them, they recombine to form ethane. They form ethane. Okay. So that is how we get chloromethane. So just have a look at this carefully. Okay. Now, when all the free radicals are consumed, when they are finished, when they recombine with each other, okay, then the reaction gets terminated. So I will advise you all to please practice this mechanism, which is called free radical mechanism for the reaction of alkane with halogen. Okay, so after that, moving to the next slide over here. This is also important, very important. Reaction of alkanes with oxygen in presence of a catalyst, where formation of alcohol happens, aldehyde and carboxylic acid also happens. So here, alkanes on complete combustion gives carbon dioxide and water vapor. Okay. During incomplete combustion, alkanes give carbon black, which is used in the manufacture of ink or printer ink, black pigments, and as fillers in tire industries. There is incomplete oxidation. There is carbon. Okay. Otherwise, from here, if you react an alkane with oxygen in the presence of copper catalyst, copper tube, okay, then it forms an alcohol, methanol. Okay. If the catalyst used is molybdenum oxide, then it is an aldehyde. If the catalyst used is manganese acetate, then the product is an acid, carboxylic acid. So you're getting an alcohol, you're getting an aldehyde, you're getting an carboxylic acid. Okay. So this way. So you have to remember this is important. This reaction is important. Now, ordinarily, alkanes resist oxidation, but isoalkanes 3-degree hydrogen on oxidation with potassium permanganate gives tertiary alcohol. So if you react a tertiary alkane like this, tertiary alkane, like for example, there is CH, okay, and there are CH3 over here, CH3 over here, and there is CH3. This is a tertiary alkane. Okay, if it is reacted with potassium permanganate, which is an oxidizing agent, so this H, it is getting replaced by the OH group. Okay, it is getting replaced by the OH group of an alcohol to give a 3-degree alcohol. So these reactions are important. Okay, reaction of alkane with oxygen in the presence of a catalyst, where we get alcohol, we get aldehyde and a carboxylic acid. Next, moving to the next slide over here, with regard to aromatization, cyclization, isomerization of alkanes. If you take alkane, this is hexane, in the presence of platinum catalyst and reaction with hydrogen gas, it forms an aromatic compound which is called benzene. Okay, okay. Otherwise, if there is no catalyst, if there is catalyst, it can also form a cyclic compound over here, cyclomethyl pentane and hydrogen. It can also undergo isomerization. It can form isomer, 1, 2, 3, 4 branched isomer. Okay. If we add hydrogen, then it can also undergo hydrogenolysis, addition of hydrogen, and dimerization over there to form C3H6 in that manner. Okay, so these three are more important. Alkenes, they can undergo aromatization, they can undergo cyclization, they can undergo isomerization. That means they can produce isomers as well. Now, moving to the next slide in this chapter, that is called pyrolysis. Pyrolysis means action of heat, lot of heat, high temperature. It is also known as cracking. Now, the decomposition of a compound by the action of heat alone is called pyrolysis. Pyre means fire, you know. Lysis means split up, cleavage of heat. The pyrolysis of alkenes is known as cracking also. Alkenes decompose into smaller molecule on heating to in this temperature range. Ethane, when heated to 500 degrees Celsius in the absence of air, gives a mixture of methane, ethylene, and hydrogen. So you can have a look at this example. Okay, I have taken ethane, I have taken propane. When they heated to over here 500 degrees Celsius in the absence of air, then ethane gives ethene. This is ethene, this is ethene. Okay, this one is ethene, and this one is propene over here. Along with ethene, we get methane and hydrogen also. And if you are using a propane, then you're getting ethene plus, this is propane plus this one is ethene. Okay, so breaking down into its simpler components by reaction of heat on alkanes, it is called pyrolysis of cracking. So you should be able to figure out what could be the products. Here I will ask indirect questions. Okay, so I'll ask a question like this. For example, what are the products, or suggest possible products obtained when propane is subjected to 500 degrees Celsius in the absence of air? So what should be the answer? The answer should be ethene and propene. Ethene and propene along with methane and hydrogen gases as well. So this breaking down, splitting up into smaller components of the alkanes because of high temperature, because of the action of heat, it is called pyrolysis or cracking. Now, after that, coming to the uses of alkanes according to number of carbon atoms, this chart becomes very important for you all, because I have seen plenty of questions from here also. The first four alkanes are used for heating, cooking, and electricity production. The main component of natural gas are methane and ethane. Remember that. Okay. Next one, propane, that is 3 carbon atoms, and butane, 4 carbon atoms, are used as LPG in our liquefied petroleum gas, which is used in the household kitchen. Propane is also used in the propane gas burners in the lab. Butane is disposable cigarette lighters. You know, cigarette lighters, you have seen cigarette lighters, no? So those lighters are filled with butane. Okay, then they are also used as propellants in aerosol sprays, you know, spray, body spray and all those things. They are used as propellants. When you press the button, it sprays the perfume or the deodorant, okay, as required. Alkanes having carbon number 5 to 8 are liquids, but they are volatile. They are used as fuels and as good solvents for non-polar substances. Alkanes having carbon between 9 to 16 form the major product of diesel and aviation fuels used in aeroplanes. Alkanes from 17 carbon upwards form the most important components of fuel oil and lubricating oil, also used as anti-corrosive agents in industries. Heavy machinery and all, they are lubricated by using alkanes containing 17 carbon atoms and higher. as their hydrophobic nature means that water repelling characteristic is high. Because of that, water cannot reach those machine parts in the metal surface. Many solid alkanes find use as paraffin wax, also candle wax. No? When alkanes with 35 or more carbon atoms are used for road surfacing, that is coal tar, metalling of roads, so contain alkanes which contain more than 35 carbon atoms. After that, synthetic polymers, synthetic polymers such as polyethylene, the plastic bags which you use normally, they are what? They are alkanes with chains containing hundreds of thousands of carbon atoms. So polyethylene is, we have this linkage is there, CH2 link is there between a long chain of CH2. Okay, that forms polyethylene. Okay, so these were some very important uses of alkanes according to the number of carbon atoms, and mm, please go through it very very carefully because you will find questions from here also. Okay, now we move to the next part of the chapter, that is the second homologous series of hydrocarbons, which is called alkenes. Now first question is, what are alkenes? What are alkenes? Now alkenes are the second homologous series of hydrocarbons. The common family of hydrocarbons found in crude oil is the alkenes. Alkenes are also called, I believe you remember, they are also known as olefins, oil forming. In this family, there is at least one carbon-carbon double bond. This double bond makes a big difference to the chemistry of the compounds of this family alkenes. Okay, so the alkenes and particularly ethene are tremendously important in the chemical industry. They are not found in crude oil in very large quantities, but are produced by the cracking of the alkenes. So if you break the alkenes down, that time you saw one example, CH3, CH2, CH3. If it was heated to 500 degrees Celsius, then it broke down into what? It broke down into propene. It broke down into propene. One is propene. It broke down into ethene. It broke down into methane, and then after that hydrogen. Okay, so these are the products formed. Now the alkenes, like all the hydrocarbons, burn in air to form carbon dioxide and water if there is no catalyst. In oxygen, ethene reacts explosively so that it is not much good as a fuel. So we cannot use it as a fuel. The alkenes are also too useful in the chemical industry for the manufacture of plastics and many other chemicals to be used as fuel. So this is an introduction about what are alkenes. Okay, what are alkenes? You can figure out the answer from this slide. Now, moving to the next slide regarding the nomenclature of alkenes over here. Similar to that of alkanes, except the ending of the root name corresponding to the longest continuous chain containing a double bond is changed from ene to ene. This is the only difference in the IUPAC nomenclature of alkenes. The N becomes in over here. Example, ethane becomes ethene. Propane becomes propene. Cyclohexane becomes cyclohexene, and so on. So when a chain contains more than 3 carbon atoms, a number is used given the position of the double bond. So we have to name the double bond. So here over here, you cannot number from here, you have to number from here because the double bond is closer to this carbon. So 1, 2, 3, 4, and 5. So it is what root is pent, and the second carbon atom is having the double bond, so pentene. You can write pent 2 in also, pent 2 in also, that is also correct, and this one is also correct. You can write either way. Okay, now coming to some examples of nomenclature of alkenes, you can see on your screen I have given only selected examples which are generally asked in your examination class 11. Okay, these are the selected examples which are generally asked in the class 11 final exam as well as the competitive examination. So if you look at this, numbering has been done from here 1, 2, 3, 4, 5. So it is one pentene or pent 1 in. The second one, if you look at the second one over here, numbering is done from this carbon atom. So 1, 2, 3, 4, 5, 6. It is hex in. So you can name it as 2 methyl hex 2 in. 2 methyl hex 2 in. The third one, it is not numbered from here, it is numbered from here 1, 2, 3, 4, 5, 6, 7, 8. So here the third carbon atom is having a triple bond. That is for the case of alkynes. So this I will discuss later on. Okay, so these are few examples. Look at the next screen over here. On your screen you have a structural formula, condensed structural formula of an alkene. Now I am giving you 2 minutes. Please name this compound according to the IUPAC rules. Name it and tell me the answer. Do the working in your exercise copy somewhere. I'm waiting. Yes, anybody? Anybody getting the name? From which end will you number? First, decide that. From which end will you number?
Right.
Huh?
So right end.
Why right end?
So because there is a double bond there.
Yeah, you'll number from this end, right end, not the left end. Because there is a double bond closer to this right terminal carbon. So 1, 2, 3, 4, 5, and 6. The double bond, the presence of a double bond dominates the side chain branching. Okay, so it's numbered. So now number it quickly and tell me the answer. Tell me the answer. The hex is the word root. 2 in is the primary suffix and 5 chloro is the prefix. So the IUPAC name of this compound is 5 chloro hex 2 in. Okay, please follow my method. Okay, you can write 2 hexene also, but that will be obsolete when you go for a higher IUPAC nomenclature. So just follow this method, this order. 5 chloro hex 2 in.
Sir,
Yes.
sir, bond even dominates the functional group, no, for numbering
Yeah, that
carbon.
time bond also dominates the functional groups. Okay. So remember, multiple bonds they will dominate. They will dominate. Okay. Got it. So did you understand this answer? 5 chlorohex 2 in. Am I clear?
Yes,
Okay.
sir.
Shall we go
Yes,
to
sir.
few more examples? Okay. Now let us look at some more examples of nomenclature of alkenes. Okay, on your screen. Look at the first one. It is an alkene, but it contains two double bonds. Two double bonds. So numbering has been done from this end. 1, 2, 3, 4, 5, and 6. That is why it is hex hex diene 1 4 hex 1 4 diene. You can write it this way also. Hex dash 1 comma 4 diene DIEN hexa hexa. We write hexa hexa 1 4 diene also. This is correct. This is also correct. Okay. Now look at this one. The second example. It contains double bond as well as triple bond. See, it contains double bond as well as a triple bond. So, numbering has been done from which end? Numbering has been done from right end over here. One,
Left.
not left. Just check. It has been done from the right side.
Yes,
One,
sir.
two, three, which means the double bond, it is dominating the triple bond also. Yes or no? Yes or no? One, two, one,
Yes, sir.
two, three, four, 4, 5, and 6. So keep this in mind. So the answer becomes uh, X 1 3 diene 5 ein. X 1 3 DIEN diene, then 5 ein YNE. Okay, this is also correct. This is also correct. Okay, second example. And there are other examples also again over here. 3 pent 1 in. No, pent 3 in. Numbering has been done 1 2 3 4 5. So
Sir,
here, yeah, tell me.
sir, that Y is not a vowel. No, why is that E removed from last?
No. This it is pent ENE. No, here This one actually they have done this way, right? Okay, pent 3En, then 1YNE. Pent 3En 1INE, because this one it is not a vowel, so there's no need to put the ENE. There's no need to put ENE over it. Okay. In this case, that rule will not be followed, which I had told earlier, no, because this is not a functional group, no. It's not a functional. It is it belongs to the same primary suffix only. So it is pointless putting the ENE over there. No need to put ENE. Okay, we just shorten it and write EN. It is understood. It is an alkene as well as an alkyne. Okay. Similarly, there are,
Can we put ENE also?
you can put ENE also. That is also correct. Pen 3 in dash 1 in. You can put ENE also. Okay, that is also correct. Okay. Now look at the next example again. 5,5-dimethyl 1-hexene. Okay, this is actually X1 in, 1 2 this way, no. Then carbon 5 has 2 dimethyl methyl groups, so 5,5-dimethyl 1-hex1 in. That is also correct. And there are other formulas over here, which this one you can leave it out. This is for higher chemistry. And this one is a cyclic compound. This also you leave it out. Okay, this one you don't do. Others you can practice. It will help you make better. Okay. After that, after the nomenclature, let us move to the next slide over here. Structure of a double bond in alkene. Here on your screen you can see there is an what you call ethene. There's an ethene, ETHENE, ethene molecule. Ethene molecule is like this: carbon carbon double bond, hydrogen hydrogen, hydrogen and hydrogen. Okay. Now one is a sigma bond, one is a pi bond. Okay. So here this bond which you see, that's a carbon sp2. The carbon, each carbon is sp2 hybridized. Each carbon is what? sp2 hybridized. Okay. And that's a carbon sp2 carbon s2 sigma bond. This first one is a sigma bond. And then when the orbitals, the p orbitals, which contain electrons, they overlap sideways, not head on, sideways, which result in the formation of a pi bond. So this one is a pi bond. Okay. That's a single pi bond. So that is how the structure of a double bond in alkene looks like. Okay. So here, what is the question they will ask? What is the question they will ask? They will ask you, what is the hybridization of this carbon atom in alkene? What is the hybridization? It is sp2. It is sp2. That is the question they will ask from here. Okay. And this one is a p orbital. This also p orbital. That is a pi bond. And this one is a sigma bond. Okay. Now, after that, moving to the next topic over here, which is called isomerism in alkenes. Now, this is the entire isomerism which is happening in alkenes. Okay, I'll show you a better picture after this. Now, in alkenes, isomers, there are two types. One is constitutional, depending upon which functional group is there. Another one is stereoisomers. Under stereoisomers, we'll have plenty of them. One is configurational, directional. One is conformational, like you saw the Newman projection formula that way. Under configurational, geometric, when there are double bonds, and under configurational there is optical, because of the rotating the plane of polarized in different directions in clockwise and anticlockwise. We have enantiomers and diastereomers. So this will be discussed again once again in the chapter class 12 chapter organic chemistry. Okay, so here this is just a brief picture of the happening of isomerism in alkenes. Okay, so moving to the next slide over here, we'll just check the chain isomerism and position isomerism in alkenes first, which are important. So here, if you look at this first set of examples, if you look at 1-butene or 2-methyl-1-propene, these two are isomers. Okay, this is a straight chain, this is branching, so these two become isomers. Again, if you look at 2-butene, okay, and this 2-methyl-1-propene, these two again isomers separately. Okay, what type of isomers? They are chain isomers, but 1-butene and 2-butene, these are position isomers. Position, because the position of the double bond is changing. This one is actually 2, this one is 2, this one is 1. Okay, the position of the double bond in 2-butene and 1-butene is changing. That's why they are position. And if you compare 2-butene and 2-methyl-1-propene, it is branching over here, but there is no branch over here, so it becomes chain isomers. Okay, so again, a similar example, you can see the same thing. It has been explained over here also. This is
Excuse
going,
me, sir.
yes,
Sir, how can we know how many types of chain isomerism will be present?
by drawing the structures like over here. No, if you're talking about
Yes,
position
sir.
isomers, in this case of butene, we can have two isomers, two
So because
isomers.
in the book there were some questions, no sir, they were saying there 9 isomers were there.
Now that depends on the number of carbon atoms. If the
Yes, sir.
number of carbon atom increases, no, if you go beyond 5, 6, 7, 8, the more the number of carbon atoms, on that basis we can calculate or find out the number of isomers possible for that corresponding alkene. Okay, but here in this case, you see clearly, very clearly over here, this one and this one, these are position isomers. So only two are possible, no? If I put it here, it becomes this isomer. If I put it here, it becomes the
Yes,
same
sir.
isomer only, no? So two isomers possible. And this one and this one, again two isomers, because one is a straight chain, another one is a branch chain. So again, what do you call this chain isomerism? Also two types of chain isomers are there. Okay, so that is what alkenes exhibit isomerism in these two different manners. One is chain isomerism, another one is position isomerism. Now the other type of prominent isomerism which is exhibited, that also I'll discuss after some time, but let me clear this properly. Now, with regard to position isomerism in alkenes, over here, look at this example, X1 in, where number of carbon atom is more than 4. It is 6 carbon atoms. In the first one, you can see the double bond is between the first and the second carbon. In the second one, it is between second and the third carbon. And in the third one, it is between third and the fourth carbon. So there are only 3. If you put this over here, then it is the same thing, X1 in only, because you start counting from here. Okay, so if you put this here, it is the same thing, X2 in only. If you put this here, it is the same position, it will be X3 only. So for hex in, the isomers possible are 3. Position isomer possible are 3 of them only. Okay, so alkenes exhibit chain isomerism, they exhibit position isomerism, as well as one more type of isomerism which is called geometric isomerism in the form of cis and trans designation, which you can see on the screen. But for geometrical isomerism, the presence of a double bond and groups around it, around the two double bonded carbon atoms, there should be groups around it which should be different. Say for example, if you look at this pent-2-ene over here, this hydrogen and this hydrogen are below the double bond, are on one side of the double bond. Okay, so that's why it is called cis. Cis means what? Same side, on the same side. Okay, but the same thing is drawn in a different manner over here. The hydrogen, this hydrogen has been taken over here, so they are on opposite sides, diagonally opposite sides of the multiple bond. So here it becomes trans. Trans means opposite sides, like a diagonal. Okay, so this is one example of geometrical isomerism where the two isomers are called either cis or trans. Another example is given by this example, chloropropene. There is a chlorine over there, so the two hydrogens like groups are on the same side, unlike groups on the other side. Over here, see, now the like groups are on opposite sides. That's why it is trans isomer. It is called trans chloro 1 chloropropene or trans 1 chloropropene. Okay, so the number of isomers which is exhibited by alkenes is chain, position, and geometrical isomerism also, according to your syllabus. Okay, now after this, moving to the next slide regarding the methods of preparation of alkenes. Alkenes can be prepared by the following general methods. Like first one is dehydration of alcohols, dehydrating agent, by using a dehydrating agent like concentrated sulfuric acid, or we can use in place of this phosphorus pentoxide also in place of sulfuric acid. So if you dehydrate an alcohol, you will get an alkene. Generally, water is kicked off. The next one is dehydrohalogenation of haloalkanes. If you take a haloalkane, an alkane containing a halogen, and dehydrohalogenate it by using sodium hydroxide, alcohol, okay, and reflux it, then what happens? Both halogen and hydrogen is removed from here. Halogen from this carbon and hydrogen from this carbon is removed, and that's how we get an alkene, and HX is formed as a byproduct. So these are the first two methods of preparation of alkenes, and remember them in this way: dehydration by using Kong sulfuric acid or phosphorus pentoxide, or dehydrohalogenation, means removal of hydrogen and halogen both. So that is called dehydrohalogenation of haloalkenes. So for this, you can have a look at an example over here. I can have CH3, CH2, CH2Br. Okay, then I'll use alcoholic potassium hydroxide, alcoholic, not aqueous, alcoholic, in ethanol medium. This is potassium hydroxide. So when this is subjected to alcoholic potassium hydroxide, bromopropane, then this bromine goes away from this carbon and the hydrogen goes away from this carbon. So we get CH3, CH, then there is a double bond, and then CH2. Plus we get KBr plus HOH. Okay, so this is an alkene. It is prop 1-ene. So that is how we prepare an alkene by this method. Now, moving to some other methods of preparation of alkenes we have on your screen, which is called preparation of alkenes by Kolbe's electrolytic method. Okay, so for Kolbe's electrolytic method, we can use a salt which is called sodium succinate. Sodium succinate. Okay, and in aqueous solution, the ions present are succinate ion and sodium ion. The ions separate. Okay, now at the anode, the anion will go to the anode. It will lose 2 electrons, and will form this succinate. It is unstable, so it will form ethene. It will remove the carbon dioxide. This carbon dioxide gets removed from here, and the double bond formation happens over here to give ethene and carbon dioxide liberated at the anode. And at the cathode, the cation goes to the cathode, where two sodium cations, they gain 2 electrons, these 2 electrons over here, and form sodium metal. This sodium metal combines with the water which is present in the electrolyte to give an alkali, a strong alkali, that is sodium hydroxide, and hydrogen gas is liberated at the cathode. So you must remember the reaction only, not the experimental details of the Kolbe's electrolytic method. So the equations are very important over here. Okay, starting from sodium succinate. So the aqueous solution of sodium succinate giving succinate ion. After that, the succinate ion goes to the anode, discharges over there by losing electrons to form ethene, carbon dioxide. Whereas at the cathode, the sodium cation, it is gaining electrons to form sodium metal, reacts with water in the solution to give sodium hydroxide and liberate hydrogen gas. Okay, so this method is also important. Now, I think it is already time up for today. Okay, it is already 12:40. So I would like to end my class here only. I'd like to end my class here only. So just hang on, because I need to record the attendance well, okay, for today's class. Okay, just a second. Okay, your attendance is being downloaded. It is downloaded already. Okay, thank you so much. Have a nice day.
Thank you, sir.
Sir,